So our second talk in the afternoon is going to be given by Navin Goyal. He's from Microsoft Research and he's interested in theoretical computer science problems and also algorithm problems arising from practice. He's going to tell us about Polytope learning problem.
Okay, thank you for the introduction and thanks to the organizers for giving me a chance to speak here. Thanks for coming. So this is going to be a theoretical talk, and this is based on joint work with Luis Rademacher. I've taken the title of this workshop literally, and I'm going to focus on a computational challenge. I'm not going to tell you about any new results. This will be a survey-like talk, so I'll tell you about this problem and its connection to various other problems, well-studied problems, and some approaches and partial results. Okay, so let me start with a more general problem, the problem of learning convex bodies. Very simply stated, there's an unknown convex body K in a d-dimensional Euclidean space. It's full dimensional, so it's not restricted to any subspace. And what we get as input is uniformly random samples, x1, x2 from K. And the problem is to reconstruct K. So let me make this more precise, what I mean by this. So our output is a set K prime that is close to K in the following sense. So U sub K is the uniform probability density on K, and U sub K prime is the uniform probability density on K prime, and they are close in L1 distance, very natural motion. And we allow improper learning. So K prime is given by a poly D time oracle. So given any point X, the oracle tells you in poly D time whether X is in K prime or not. So it could be a neural net or polynomial threshold function or anything. Okay. So that's the problem. We are interested in minimizing the number of samples that are needed, statistical complexity, and how much time is needed. So let me remind you that the Peck learning of convex bodies is hard because the VC dimension of convex bodies is unbounded. But what we are doing is we are fixing the distribution, which is uniform on the body. So it is actually solvable. And we're interested in whether how many samples are needed and how much time is needed. And this can be thought of as an instance of the density estimation problem. So we are only given positive samples, unlike in Peck learning where we get positive and negative samples. But we have this restriction on the density that it's a convex, it's a uniform distribution convex body. Okay, so what can we say about this? So in constant dimensions, we can solve this problem by just like in the plane, we can just fit a piecewise linear curve, convex curve, and that does the job. And similarly, in high dimensions, we can again fit piecewise linear surfaces. But its complexity seems to scale exponentially with d. So that's not very useful. So intuitively, one feels that in high dimensions, there's too much room and the problem is inherently hard, in the sense that if you have the cube, then it has 2 to the n corners, and you really have to go there and check if the corner is there or not. Otherwise, you don't know it's there, so you can't really solve the problem. But let me remind you of the result of Diaphragm-Cannon, which shows that interesting things can happen in high dimensions if you have randomized algorithms. So volume computation of convex bodies can be done in polynomial time, but they assume a stronger access to the body, which is the membership oracle, not just random points. And so membership oracle is just that for any given x, the algorithm can ask the oracle whether the point x is in K or not. And they give a polynomial time algorithm for solving this problem, and also for generating random points. So this is a stronger access. So we could ask if our problem is hard if we give stronger access to the algorithm by providing it the membership oracle. Okay, so you want to learn convex bodies under membership oracles and random points, polynomial time, polynomial complexity, sample complexity.
Sorry, why can't you just output the oracle as the answer? What does it mean to learn?
Yeah, so we can't, okay, I guess we can't do that. We want to have our own set, which you can make polynomial number of queries, and then you have to answer all the next the new queries that come. So that's not clear, right?
Like a sample based on the sample.
Okay, so it is actually hard. The intuition I gave earlier sort of makes sense, and the result is that you need to do the square root of d over epsilon samples. So this is sample complexity lower bound to learn convex bodies, and this was done in 2 different papers. So how do you prove such a result? So essentially, what you have to do is you have to construct a large family of convex bodies. Large is very large, it's W exponential in D, which have these 2 conflicting properties. So any 2 bodies in the family are far from each other in the L1 distance sense. But if you just make polynomial number of queries, either membership or random points, then after you make polynomial number of queries to a body, there will be still many other bodies in the family which will be consistent with the queries that you made. So polynomial number of queries are not sufficient to tell apart your body from other bodies in this family. So the construction of this family in the second paper is very simple, and I'll tell you right here. It's just intersection of random half spaces tangent to a sphere. Right? So you take a sphere, and I'm not going to tell you the parameters here, and you just draw uniformly random half spaces, exponential in D, or square root D, and that gives you one convex body. And you do this experiment many times, and that gives you the family. And with some constant probability, this is going to satisfy those conditions.
Can I ask a quick question? So how is your algorithm problem related to the algorithm problem of those guys, Clive Watson, Thomas, and Navin?
I'm going to mention that. So their problem is about when you put the uniform distribution on the ambient space, not uniform, sorry, Gaussian, and then you do pack learning. So you get positive and negative samples, and you want to learn the body.
Yeah, that's why. So isn't that problem easier than yours because you only have positive examples, you probably have one positive?
So that's not clear, I will say, because in our case, somehow the distribution adapts itself to the body, and that can be useful. It's uniform on the body, and that can provide useful information sometimes. So I'll show you some results where we can solve the problem, but it can't be solved in this model. We don't know how to solve it in this model. So I don't know exactly what's the relation between the 2 models. Okay, so that's the construction, but it's a little hard to provide intuition for this. So I'll tell you the construction from the other paper, which is also quite simple and maybe a little easier to provide intuition for. Okay, so we'll start with the cross polytope in RD. This is just the convex hull of the plus minus 1 standard unit vectors, or the L1 ball. This 2 to the d facets, 2d vertices. And now we can attach a pyramid of fixed height to the facets of this, right? So it's like attach this pyramid here or anywhere, the same height. And I choose the height so that if I attach all the pyramids, the body is still convex. So I find the maximum height so that it still remains convex. Okay. And now my hard family is going to be the convex bodies you get by attaching pyramids to any subset, right? So you have 2 to the d subsets, and each of them gives you a convex body. Now, to learn the convex body, you basically want to find which of the pyramids are there or not, and you have to go and check for them, otherwise you don't know. So you have to make exponentially many queries. So polynomial number of queries are insufficient to determine which body you got after. Yeah. So, but this does not quite work because the total number of total volume of all these pyramids can be at most 1 over d fraction of the volume of the cross polytope. So if you just output the cross polytope as your answer, that would be a good answer for this family. So this family doesn't quite work. But there's an easy fix for this, which is hardness amplification using tensor product, so or this Cartesian product. So we take new convex bodies in r to the square root d, and we take these cross polytopes with pyramids and take the Cartesian products for these bodies. So this gives us a new family and satisfies both the conditions that we had before. Okay, so learning convex bodies is hard. I should tell you about this. So Loas asked the question whether the volume can be estimated from polynomially many random samples. And that's, you can't actually do that. There are exponentially many samples needed to do that.
So that was known, right, for a long time?
No.
That second line?
No.
Is it like fully exponential instead of something?
No, that's not the point. It was not known. Maybe you're thinking of deterministic algorithms. That was known for a long time.
I see. For random samples, it was not known. I see.
There's no oracle, only samples.
Got it.
So all these convex bodies have very complex boundaries, exponential number of facets. And that's what seems to make them hard to learn. So it would be interesting to restrict our family of convex bodies. So one of the canonical class of convex bodies is polytopes with m facets, or this is basically intersection of m half spaces. There's small VC dimension, m polynomial in m and d. So we can do pack learning in terms of sample complexity with poly MD samples. But computationally, we don't know how to do this. We don't even know how to do it for two half spaces. And there are many cryptographic hardness results. There are algorithms for learning intersections of M half spaces under fixed distributions, log concave distributions, Gaussian distributions. So for Gaussian, the best result so far is the minimum of d to the log m over epsilon square and m over epsilon to the m. So it's not polynomial in d and m.
So for two half spaces, which computational hardness results are you referring to?
That we don't know how to do that, but in general there are computational hardness results for many half spaces. Yeah.
But not for two, right?
Yeah, I'm not sure if there is one for that. Okay, so for Gaussian, there are pretty good algorithms, but they are not polynomial yet in D and M. And our problem is uniform on the polytope. So we only get positive examples, and we have to put this extra condition, which is not very important really, is that the intersection is bounded. In the case of intersection of half spaces, there is no boundedness condition. And it also means that our number of facets has to be at least d plus 1. Okay.
For Gaussian, it's m to the log n times 4.
Okay, I'm sorry. Yeah, that's after your direction. Yeah, right. So let me just restate the polytope learning problem. We have a polytope, unknown polytope P with at most m facets. We get poly number random samples, and we want to efficiently reconstruct P. Yeah. So let me just mention one more aside. What if we allow ourselves membership oracle in this case? And then this problem was studied a long time ago, and you can pack learn in polynomial time. This is the result of Quack and Pitt in 97. Okay, but we are interested in that problem. Okay, so let me tell you where we are in the talk. I told you about learning convex bodies, polytope learning problem, and now I'm going to talk about some approaches and partial results. The first approach, so far I haven't actually said why the sample complexity of this problem is polynomial, right? So it does not immediately follow from pack learning result, even though the VC dimension of this class is small, but that does not immediately imply that the polytope learning can be solved with polynomial number of samples. But it follows quite easily from VC results. So the way to solve this problem, the sample complexity problem, is we take the minimum volume polytope Q that contains all the samples and has at most m facets. Why is that a good reconstruction? Why is that a good solution? So first we observe that if P1 and P2 are two polytopes with at most m facets, then VC dimension of the class, which is the difference between two polytopes, is also the same, dm log m. Now, for the minimum volume polytope Q, its total variation distance from P can be rewritten as the volume of P minus Q over the volume of P. And this requires a little bit of computation, but uses the fact that the volume of Q is at most the volume of P. And then we just use the VC theorem, VC uniform convergence theorem, to say that these two things are approximated by the sample point. They are proportional to the sample points not in Q and number of sample points, total number of sample points. And we know that this number is 0 by our construction of Q. So this number is small. So Q is a good approximation of P. But how can we find this polytope? It turns out that even finding the smallest volume enclosing simplex is NP hard. But that's not a hurdle for us because our data is not worst case. It comes from a structured distribution. So we can try to find various heuristics to use that structure, but we have not succeeded. And we don't even know how to learn the class of cubes using this approach. But the cubes can be learned using a different approach, which I'll tell you about now. This is the method of moments. It's a general method for estimating the parameters of probability distributions. You estimate the moments, mean, variance, covariance, and other statistics of the sample, and then you try to find the parameters that produce those estimated moments. This was first used by Pearson to learn mixtures of Gaussians. So how do we apply this method for our problem? So it follows more generally, parallel pipettes can also be learned. So let me be a little more precise about what I mean by learning these things. So here we are given samples from a parallel pipette, which is x equal to as plus b. X and s are random variables in RD. B is a vector, and a is a non-singular matrix. And s is uniformly random in the cube. So basically, we are taking the cube, we are applying a linear and affine transform, and we get to see the samples of x. And we want to reconstruct the parallel pipette. In this case, we'll do proper reconstruction. Okay, I'll come back to that. So we'll do proper reconstruction by estimating A and B. So here in this picture, I'm just saying that there is some parallel pipette somewhere, and we get random samples. But we only get to see the samples, and we want to find where they came from. And this problem reduces to learning cubes. The hard part is learning cubes, so we can assume that A is a rotation matrix and B is 0. So I'll focus on this problem from here on. There's an easy reduction from parallel pipettes to cubes. Okay, so this was shown in two different communities, Fries, Jerome Kuhn in computer science, and in signal processing, it was more or less well known for a long time. So the algorithm they gave is very simple. So we define the fourth directional moment of the cube in direction B. And for now, let me assume that the cube is axis parallel. For the moment, let me assume that. So in direction B, the fourth moment is the expectation of v dot x to the 4. X is a random sample from the cube. And when the cube is axis aligned, there's a very simple formula for this. It is just a constant minus another constant times the sum of the fourth powers of the coordinates of v. Okay. So we can draw this here. This is a polar plot for the function f of v. In direction v, this distance is the value of f of v, right? And you can see in this picture that the local minima, as v varies over the sphere, the unit sphere, the local minima of f of v are exactly these 4 points. And they correspond to the facets of the cube, right? So if your cube was not axis aligned in general position, then the fourth moment would also rotate in accordingly. And by finding the local minima, we would be able to find the facets. And so we'll be able to find the matrix A, and that will solve the problem. And we can estimate these directional samples from polynomial number of moments. And local minima can be found efficiently by projected gradient descent. So this solves the cube learning problem. So Fries-Jerome-Kunnen asked about learning polytopes. This is probably the first instance where I know this to be the first place where the problem was asked. In particular, they asked about learning simplices. So we showed that simplices can be learned efficiently. Let me contrast this result with the problem of learning, packed learning when the distribution is Gaussian distribution. So there, the best algorithm requires time d to the log d. But for our setup, we can do it in polynomial time. So there is some difference between the two problems. There are results for training neural networks, particularly this result, which works for one hidden layer, but does not seem to be applicable to our problem because the top gate there is a sum gate, and I don't know how to make it work for our problem. So let me say a little bit about proof. We give two proofs. The first proof is just basically the same thing as what we saw for the cube. We use the third directional moment. But the problem, the reason FJK didn't do it was probably that the computation of the polynomial becomes harder, even though it's lower degree. But morally, it uses the same general ideas. The other proof is the reduction from independent component analysis, reduction to independent component analysis, and we can also do other bodies like LP balls or in particular the cross polytope. So let me quickly say what independent component analysis is. It's a very well-studied technique in signal processing and also in many other areas. So we have this model. X is a random variable given by A times S. A is a non-singular matrix, and S is a random variable. What we know about it is that its components S1, S2, SD are independent. And they are not Gaussian, but we don't know their distribution. And we also don't know the matrix A. We are given samples of X, and we want to estimate A efficiently. So that's the ICA problem. Our problem, learning cubes, is a special case of this. Right? When S is uniform from -1, 1 to the D. So the results of Fries-Jerome-Kunnen and the other papers actually apply to ICA, so they solve a more general problem. So let me just very quickly say how we reduce learning simplices to ICA. So standard D-1 dimensional simplex in RD. So it's a D-1 dimensional simplex, but we embed it in RD. It's just the usual thing. Sigma of xi is 1, and all the variables are non-negative. Then if you have a uniformly random sample from the simplex x, and R is a scalar random variable with density proportional to x to the D-1 times e to the negative x, then Rx has independent non-negative components. So it basically, the problem becomes independent component analysis problem after you do this multiplication by this random scalar. So that's all I'll say about this reduction. How much time do I have? 15. Right. So tensor decomposition methods are another way to utilize the moment information. It's not very different from polynomial optimization technique that we just saw. But they have been recently very popular for latent variable models. So I'm going to skip this part. I was just explaining here an example of how tensor decomposition is used for solving ICA. It is, but here I want to just point out that learning simplices turns out to be a special case of latent directly allocation, which we saw in the first talk of the workshop. And LDA was shown to be learnable using tensor decomposition around the same time by Anand Kumar, Foster, Shu, Kakade, and Liu. So this is another connection of polytope learning to a fairly well-studied problem. So we didn't know about these things, and we were quite surprised to learn about these connections. And tensor decomposition has been used for many other problems recently, hidden Markov models, mixtures of Gaussians. Okay, but our main interest is in whether we can use the method of moments to learn polytopes, more general polytopes, right? So far, what I showed you is that we can learn cubes, simplices, cross polytopes. All of them share the property that they are highly symmetric. And in some sense, these are the only symmetric polytopes in high dimensions. But when we go to more general polytopes, the symmetry is lost. So if we change this, if I deform the cube in some way, then my fourth moment will deform. So if I change this thing here, then it's going to make changes over here as well. And I'll not be able to find the facet as local minima of this side. So making changes over here changes the fourth moment curve everywhere. And that seems to make it very hard to use the moment method for general polytopes. The formulas just become very complex. So we don't know how to do that. But let me mention this result, which is exact reconstruction of polytopes. Now this is for M vertices, not M facets. But this class also has small VC dimension, so it's learnable. And this can be done with first MD moments in D+1 random directions. So this uses a formula that relates directional moments to the vertices and uses a different way. It does not use optimization of polynomials or tensor decomposition, solves the system of polynomial equations, but doesn't help with our problem because it uses very high degree moments. And to compute kth directional moment, degree k moment, it seems that we need at least 2 to the omega k samples. So this result is not helpful for our problem. So the question is if we can learn polytopes with the directional moments of constant order, right? We don't want to use moments of such a high order. And these moments can be computed in polynomial time from our samples. So I'll make that question precise, and for that, let me state this simple definition. The third directional moment in direction v is just this expectation of v dot x cubed, and we can take the expectation inside. And these terms define the third moment tensor. So this is d by d by d array. Tijk is equal to just expectation of xi, xj, xk, d cubed numbers, and they can all be estimated well with poly d samples. And once we have these d cubed numbers, we can estimate this for any v, right, by plugging in the values here. And this works for all k, it's similar. The kth directional moment can be estimated from kth moment tensor. So here's a more precise version of the question. the method of moment can solve polytope learning. So I just put some fixed numbers here. They are not very important. Does the 100th moment tensor suffice to determine polytope with at most 10D facets, information theoretically? So we want to do it algorithmically, but even information theoretically can we do that? So more precisely, if we have two polytopes P and Q in RD, and their 100th moment tensors are the same, does that imply the two polytopes are the same? And the answer is unfortunately no. So we can construct polytopes. There are different, even though their moments, first 100 moment tensors are the same. And the construction is quite simple. So I'll give you the construction. Basically, it comes down to degeneracy. If we go to the plane, and if we look at d-gons in the plane, then they can't be determined by the 100th moment tensor. Because if you look at a d-gon, then it is a 2D dimensional object, because each point here has two coordinates. So overall, it has 2D dimensional object. And then we are taking it down to a moment tensor, 100 moment tensor, which has 100 dimensions. Right. So there are going to be polygons which are different, but they map to the same moment tensor.
If the moment tensor has size d to the 100.
No, it's e to the x1 100. We are in R2 right now, 99 and so on. We are in the plane, so right. So there are two different polygons, P1 and P2, which have the same first 100 moment tensors. And then using these two, we can lift these to d dimensions by this very simple construction. In 3D, it just looks like a cylinder. In general, we just augment these extra coordinates, which come from the cube, right? And these two polytopes have the same moments. It's a very simple calculation. Basically, it factorizes in the moments over P1 and moments over the rest of the coordinates. And these two are equal by our construction, and these are the same objects. So they have the same moment tensors. So the first 100 moment tensors can't distinguish between polytopes. So let me just connect this thing to other models that are studied and this degeneracy phenomenon. So the degeneracy issue is actually quite common in other latent variable models that are studied. In mixtures of Gaussians, the result of Kakar and Shu, which gives you efficient algorithms for large number of Gaussians, requires that the means be in general position, the means of the Gaussians be in general position. If they are not in general position, say they are on a line, then the information theoretic requirement can be exponential in the number of Gaussians. There are constructions by Moitra-Valiant, and there are more general constructions which work in considerably more generality.
So, can I ask a question? So, how is your problem related to this one? So this one is like a parameter estimation.
Sorry, problem related to what?
So, in this Gaussian mixture model lower bounds that you're mentioning, these lower bounds apply only for the parameter estimation problem.
Yeah, I'm just talking about parameter
Right,
estimation,
so
right?
Is your problem a parameter estimation problem?
Right. Yeah, so I want an evaluator, not a generator. But there is a difference here in polytope learning from what happens in the Gaussian mixtures case, in the sense that here the sample complexity is still small, even in the degenerate case that I said, because the smallest volume polytope Q, that always works, regardless of what degeneracy is there in the polytope. So there is a difference here from the other degeneracy phenomena. So can we save our conjecture, our question? So one easy way out would be to ask if moments of first 100 moment tensors suffice to determine these polytopes with 10D facets if the normals are in general position. Okay, so I don't know the answer to that. So this shows that we have to be a little, the method of moment doesn't work directly. Like if we compute the moments and then we want to get the polytope back, then that does not work, and we have to do more work. Maybe we have to work with conditional moments or something else. Okay, so that's all about the method of moments. I'll tell you about a third approach, Radon Transform. I don't have any new results here, but I think the approach is quite interesting. So I just wanted to show you. So Radon Transform is a widely used technique in computerized tomography. Here I'll just show you a special case for our situation. It works more generally. So if you are in the plane and if you have some organ that you don't have direct access to, but you can send an X-ray in any direction that you want. So suppose you can send X-ray along this line, and on the other side you can check how much the signal was attenuated. So then you can figure out what the distance along this line is, what the length of the intersection is. Radon transform is a function that maps these lines to the distance of the intersection. Okay, so radon transform of K evaluated at line L is just the intersection length. And the question is, can we recover K given the value of radon transform at all lines? And this answer turns out to be yes. There's a formula for reconstructing K from the radon transform. And this works in higher dimensions too. But in high dimensions, I will not work with what is probably the more natural generalization, where you take the convex body and you take the length of intersection with a line. Instead of a line, we will work with d-1 dimensional hyperplanes. So the radon transform now is a function from the hyperplanes to reals, and it's just the value of the area of the intersection of the hyperplane and the body. Okay, so let me just show you an example of the inversion formula, what it looks like. I'll not do anything with it. This is in R3. So so this is the radon transform if P is a plane, then this is the area of the intersection. And then we can define this, what is called dual radon transform. And this is a function of points in the space. And it is a very natural thing. It's just at any point X, you take all planes that pass through it and take the value of radon transform there and integrate it. Then we can reconstruct the body with this very simple formula. Once you have this dual radon transform, we apply the Laplacian operator, and that magically gives the indicator function of the convex body K. Okay, so can we apply this? How can we apply this to our problem? And there is a similar formula in higher dimensions. So there is some chance of applying it to our problem. But for that, we need to know the value of the radon transform for all hyperplanes. But that can be estimated easily because the radon transform over the volume, I'm sorry, this should be the volume of the body, is basically, it can be approximated. So we want to know the volume of this intersection. So instead of that, if we take a band around it, very thin band, then the volume of this so the area of this intersection times the width is a good approximation of the volume of this band, right? And that volume is approximated by the number of points, sample points that lie here. So we can use that to approximately compute all of those numbers. And this holds for all hyperplanes by the VC, by the uniform convergence theorem for VC classes. Okay. So we can approximately compute the Radon transform for all planes. And then we can invert by the inversion formula, and we can learn the convex body, right? But of course, that can't work. And the problem is that Radon transform is very sensitive to errors. It has been very well studied in 2 and 3 dimensions. But in higher dimensions, I don't know much about how to handle the errors. And the second hurdle is the computation of inversion, which involves formulas, integrals over the unit sphere, high-dimensional unit sphere, and multiple differentiations. Okay, but our special case of polytope learning might be easier. So it's possible that this approach will work. Let me, it also doesn't seem to have the degeneracy problems that the method of moments did. Okay, let me conclude. So I talked about polytope learning problem, and we saw its relation to ICA and LDA. So application of the method of moments and Radon transform, they can be seen as a general type of method where we take the polytope and we are applying some linear transformation and then get some new data, and from that we are trying to get back the original polytope. And there can be many other linear transformations. There is Fourier transform, but I don't think that works here. But there may be some others. So maybe can we design other linear transforms that allow efficient solving of the problem. Thanks.
So can you also reconstruct just from lines in higher dimension?
You can, yeah, there are formulas, but we don't know how to estimate along those. And when you take the hyperplane, we can use the VC theorem to estimate the intersection area. But for a line, I don't know how to do that, the length of the intersection.
Question.
Are there similar things, not hyperplanes, but for more general, let's say algebraic?
I don't know. I don't know. It's also a well-studied object in mathematics, pure mathematics, but I don't know what they do there.
Okay, then we will have 30 minutes of break.